Video Lecture 21A, Descriptive Main Group Chemistry, Metals and Metallurgy. In Chapter 1 of the textbook, the chemical and physical properties of the main group elements are discussed. Main group elements are those elements that are in the A groups if you follow the CAS or Roman numeral numbering system for groups within the periodic table. Main group elements do not include transition metals in the lanthanide and actinide series. We will discuss properties of transition metals in a later chapter. Main group elements have regular trends that depend on their electron structure. We discussed some periodic trends in Chem 110. These include ionization energy, electron affinity, atomic radius, and electronegativity. One trend that we did not discuss very much is the metallic character of an element. Metallic character decreases from left to right across the periodic table. This follows trends in ionization energies and electronegativity. We know that metals tend to form cations in ionic compounds. This matches with trends in ionization energy. Metals tend to have lower ionization energy since ionization energy increases from left to right across the periodic table. This makes it easier for these elements to lose electrons. Also, metals have low electronegativity. That is, when they're in covalent bonds with other elements, they tend to have less electron density around their nuclei. This makes the elements in the lower left-hand corner of the periodic table the best metals. That is, they have the lowest ionization energies and electronegativities. As we look at the properties of the main group elements, we will see how metallic character changes as we go across a row in a periodic table. One of the main features of the main group elements is that they have very regular oxidation state trends. Recall from Chem 110 that oxidation state or oxidation number is a fictitious charge that we assign to elements that are in compounds, assuming that we can split the compound into total monatomic ions. For main group metals, especially those on the left-hand side of the periodic table, the oxidation states for those elements in compounds usually equal their CAS group number. Recall that the group number tells us the number of valence electrons each element within a group has. For example, group 1A, the alkali metals, all have one valence electron in their outermost shell. These elements tend to lose their one valence electron to become +1 cations. Later main group elements, those that have less metallic character, also may have oxidation states that are equal to their CAS group number. They also may have oxidation states that are equal to their CAS group number -2. For example, if we look at the group 4A metals, tin and lead, they do have a maximum oxidation state of +4. This would have the metal lose all 4 of its valence electrons. These elements can also have an oxidation state that is equal to +2. This would be the group number 4 -2 valence electrons. This is common because the group 4A elements can lose its 2p electrons and still have a full 2s subshell. The nonmetals, on the other hand, have a variety of oxidation numbers. The most positive oxidation state of a main group nonmetal is typically equal to its group number. For example, many of the group 5A nonmetals have a maximum oxidation state of +5. This makes sense since these elements have 5 valence electrons in their free state. The lowest oxidation state is typically equal to the group number -8. This follows the octet rule. Nonmetals tend to form anions, and they usually gain enough electrons so that they have 8 valence electrons, or an electron configuration equal to a noble gas. Again, looking at group 5A nonmetals, you can see that the lowest oxidation state is -3. This is the group number 5 minus 8 electrons. Both the maximum and minimum oxidation number gives these elements an electron configuration that is similar to a noble gas, thus making them stable. Many of the non-metal main group elements also have oxidation states between these two extremes, the most positive and most negative oxidation state. They usually change in increments of 2. For example, if we look at phosphorus in group 5A, we see that the maximum oxidation state is +5. We also see that phosphorus has a +3 oxidation state, which is 2 less than the maximum possible oxidation state. Unfortunately, phosphorus does not have a +1 oxidation state, but it then does have a -3 oxidation state. Perhaps looking at its next door neighbor, sulfur, may give you a better idea. The maximum oxidation state of sulfur is +4, or +6, the group number. It also has an oxidation state of +4, +2, 0, and -2, changing in increments of 2. One thing that you may also notice is that second row elements behave much differently than other elements in the same group. This is because second row elements, being at the top of the group, have the smallest atomic radius. Atomic radius increases from top to bottom as you go down a group. They also have higher electronegativity, which decreases as you move down a group. For example, you may notice in group 5A that nitrogen has many more oxidation states than the rest of the elements within the group. You may also notice that oxygen, being at the top of group 6A, has many less oxidation states, all of them being negative. This is due to the high electronegativity of oxygen. In group 7A, fluorine only has 1 oxidation state, -1, due to its high electronegativity. However, the rest of the halogens can have positive oxidation states as well as negative. We will see how these oxidation state trends play out in the chemical and physical properties of elements within their groups. But for now, we will focus on the metals. The first thing that we should discuss in terms of metals is their electronic structure. One way to describe the electronic structure of metals is to use band theory. Band theory is based off of molecular orbital theory. We'll review what molecular orbital theory is in a moment. Band theory can be used to describe electronic energy levels in many solids, not just metals. But it works very well for metals. It also works well for insulators and semiconductors. We can use band theory to describe many properties of metals, including their electrical and thermal conductivity, So how they can conduct electricity, and also how can they conduct heat. In this chapter, we'll look at band theory for metals and semiconductor elements. But first, we should review a little bit of molecular orbital theory. Here are the major tenets of molecular orbital theory. In molecular orbital theory, we combine atomic orbitals on different atoms to form molecular orbitals. The most important property of these molecular orbitals is that they allow electron density to move along several atomic centers. We call this delocalization. We also would like to note that atomic orbitals that have similar energies will combine to form molecular orbitals. For example, in the diagram to the right, we notice that hydrogen has two 1s, both hydrogen atoms to make the hydrogen plus molecular ion, or 1s orbitals. 1s orbitals are similar or the same in energy. It would combine together from different atomic centers to form molecular orbitals. Finally, we would like to note that the number of molecular orbitals formed is the same as the number of atomic orbitals used. For example, to construct the molecular orbitals for the hydrogen molecular ion, we start by combining two 1s orbitals, each coming from both hydrogen atoms. These two 1s orbitals combine to form two molecular orbitals. A bonding molecular orbital, which is lower in energy than the original atomic orbitals, and an anti-bonding orbital that's higher in energy than the original atomic orbitals. Now we're ready to take a look at band theory. We can think of band theory as combining a very large number, on the order of Avogadro's number, of atomic orbitals to form molecular orbitals for the entire solid. We can start off simple. Lithium is probably the simplest metal we can take a look at. Lithium has a single valence electron in its 2s orbital. If we take two lithium atoms and combine them, we get two molecular orbitals, one bonding and one antibonding. The two valence electrons, each coming from one lithium atom, will occupy the lowest bonding molecular orbital. We can now take this lithium 2 atom, or molecule, and combine it with a third 2s orbital. Since we're starting with two molecular orbitals and one atomic orbital, we will get three molecular orbitals for the lithium 3 molecule. One that is very bonding, or lowest in energy, one that's very anti-bonding, which is the highest in energy, and one orbital that has energy that's in between the bonding and the anti-bonding orbital. Notice that we now have three valence electrons. And again, we fill in these electrons to occupy the lowest energy orbitals first. We could continue by taking these three molecular orbitals and combining them with a fourth 2s orbital with another single electron. We now get four molecular orbitals, two that are occupied with electrons and two that are not. This would continue as we keep adding atoms into our molecule. Eventually, we would end up with a group of low energy orbitals that are very, very close in energy. So close in energy that they form a continuum, or band, as shown in the picture. We would also end up with several unfilled molecular orbitals that will also form a band of very close in energy molecular orbitals. Notice that atomic orbitals with the same L will form different bands. Since we formed the lithium band from the 2s orbitals, we would call this the 2s band for lithium, which is half filled with electrons and half empty. We call the band that is filled with electrons the valence band, since this represents all the valence electrons for all of the atoms combined to form the solid. The empty band is called the conduction band. This is because electrons can be promoted from the valence band to this empty band, which allows for electrons to move throughout the solid. This allows for electricity and heat to be conducted throughout the solid. For metals, the difference between the conductance and valence bands is usually infinitesimally small, or they overlap in energy. Lithium, as we saw from the other page, has a half-filled 2s band. It also has a 2p band, formed from the combination of the empty 2p orbitals for lithium. The unfilled molecular orbitals from the 2s band and the 2p band overlap in energy. These empty molecular orbitals form the conduction band for lithium. This conduction band is extremely close to the energy of the valence electrons in the valence band. This means that it takes very little energy to promote an electron from the valence band to the conduction band, where the electron can move more freely due to the empty orbitals. Because there is no energy gap between the conductance and valence bands, electrons and the absence of electrons or holes can freely move through the metals. This makes metals very good conductors of heat and electricity at room temperature. We now move from band theory to talking about how we get metallic elements. Most metals cannot be found naturally as free metals in nature. They're usually combined with other non-metal elements as minerals and ores in the Earth's crust. Minerals are naturally occurring crystalline ionic solids. Minerals can combine with other minerals to make solid mixtures called ores. We can think of ores as rocks that contain a high concentration of a certain mineral, which contains a specific metallic element. Here are a few examples of different ores that contain different elements. Aluminum comes from an ore called bauxite, which is a combination of aluminum hydroxide and aluminum oxygen hydroxide. Iron is most commonly found in hematite, which main component is iron 3 oxide or rust. Mercury is found in an ore called cinnabar. This is mercury 2 sulfide, which in a highly crystalline state forms a very beautiful red crystalline solid. Lead is mostly found in the ore called galena, which mostly contains lead 2 sulfide. Finally, uranium is found in an ore called uraninite or Plitchblende, which is mainly uranium 4 oxide. It's also important to note that the only elements that you would find as free metals in the Earth's crust are the noble metals. These are the metals that are towards the bottom of the metal activity series, such as gold, silver, platinum, or palladium. These elements are usually found not combined with other elements as an ore and can be mined as free metals from the Earth's crust. This means that if we want to obtain any of the other metals, we must first separate them from their ores and then reduce them to get the free metallic state. We can use metallurgy to accomplish this. In metallurgy, we study the different reactions between metals, such as the combination of different metals to form alloys. But we also can study the chemical and physical properties used to extract free metals from their minerals or ores. The metallurgical process involves 3 stages. First is a preliminary treatment that helps to concentrate a specific mineral from its ore. We then take the mineral and reduce it. This involves reducing the metal ion to the oxidation state 0, which gives the free metal. Then finally, we take the impure metal and refine it. We will talk about each of these steps individually. The first step in metallurgy is for the ore to undergo preliminary treatment. In this step, the mineral containing the metal is separated from its ore and is usually concentrated. This can either be done physically or chemically. The apparatus on the right-hand side of your screen is an example of a physical process. Water along with the ore, detergent, and an oil detergent mixture is added to the vessel. This mixture is then stirred. A froth forms at the top of the mixture. This allows a lot of the unusable material in the ore to settle to the bottom of the vessel, which can then be separated from the rest of the mixture. The desired product usually floats to the top as part of the froth and can be separated from the mixture, while the oil and detergent is recycled. There are a couple of chemical processes that we can use to do preliminary treatment on different ores. One such chemical process is called the Bayer process. This is a 3-step process that is used as a preliminary treatment for extracting aluminum from bauxite, its major ore. Remember that bauxite is a mixture of aluminum hydroxide and aluminum oxygen hydroxide. The first step in the Bayer process is to take bauxite and dissolve it in a solution of hot sodium hydroxide. This converts all of the compounds in bauxite into one compound, sodium aluminum tetrahydroxide. This allows for all of the aluminum mineral to be converted into one into one form. The second step is to cool down the solution that contains the sodium aluminum tetrahydroxide solution. When a solution is cooled down, aluminum hydroxide precipitates from the solution, while sodium hydroxide remains. The precipitate is then filtered and dried, and is then heated to decompose it into aluminum oxide and water. The aluminum oxide would be then reduced to get the free aluminum. It turns out that oxides are easier to reduce than other types of compounds containing metals. Another process that can be used as preliminary treatment is roasting. Roasting converts minerals to metal oxides by heating those minerals in the presence of oxygen. For example, we can take the mineral galena, which is mostly lead 2 sulfide, and heat it in the presence of oxygen. We then end up getting lead 2 oxide and sulfur dioxide gas. The lead 2 oxide is then used to reduce the free element, to reduce the lead into free lead. This brings us to the next step of metallurgical processes, reduction. In reduction, the metal that's present in the mineral is reduced from a positive oxidation state to oxidation state 0, which gives the free metal. We can cause reduction to occur in 2 ways. We can use a chemical reaction, or we can use electrolysis. One example of a chemical reduction is the use of carbon, which is highly abundant and cheap. You did a form of chemical reduction in your Chem 110 lab called chemical metallurgy. In this lab, you took lead carbonate and reduced it to form free lead. When you heated your lead carbonate combined with filter paper in your crucible, you first caused the lead 2 carbonate to decompose into lead oxide and carbon dioxide gas. The lead oxide is then reduced by carbon to form solid lead and more carbon dioxide gas. The solid carbon was provided from the burnt filter paper. In this reaction, lead is reduced from a +2 oxidation state to an oxidation state of 0. Carbon, the reducing agent, is oxidized from 0 in solid carbon to +4 in carbon dioxide. As mentioned, carbon is a very common reducing agent because it's highly abundant as graphite or charcoal in the Earth's crust, and it is also relatively cheap. Another way to reduce highly active metals is to use what's called the Hall-Héroult process. This process is very specific to aluminum, but you can perform electrolysis on other active metal compounds as well. The Hall-Héroult process uses electrolysis to reduce aluminum oxide to free aluminum. In the Hall-Héroult process, an electrochemical cell is set up using graphite electrodes. The aluminum oxide is dissolved in a molten solution of cryolite, which is sodium hexafluoroaluminum. This cryolite is a very strong electrical conductor and helps in the electrolysis process. The molten mixture of aluminum oxide then undergoes electrolysis with the graphite electrodes. But one main difference here is that the graphite electrodes are actually consumed during the electrolysis in the Hall-Héroult process. The anode reaction involves the graphite electrodes. Solid carbon is the carbon in the graphite is oxidized to the +4 oxidation state in carbon dioxide. At the cathodes, aluminum 3+ from the aluminum oxide is reduced to liquid aluminum. This liquid aluminum settles to the bottom of the electrochemical cell and can be siphoned off and cooled to form a metallic aluminum. The final step of metallurgy is to refine a metal. In this step, the free metal is purified using usually chemical or physical processes. An example of a physical method of purifying a metal is to use distillation for metals with low boiling points. In distillation, you would boil the metal, and the metal would separate from other impurities based off of its boiling point. Another way to purify a metal by chemical means is to again perform electrolysis. For example, copper is typically purified through electrolysis, as shown in the picture on the upper right-hand side of the screen. In the refining of copper, the impure copper is used to make one or several anodes. In addition, a pure copper sheet is used for the cathode. Again, more than one copper cathode can be used. These metal electrodes are then submerged in a solution of copper sulfate. When power is supplied to the electrochemical cell, the impure copper anode undergoes oxidation. It oxidizes copper along with any other metallic impurities into the +2 oxidation state. Elements that are not oxidized and go into the solution phase often collect as a sludge at the bottom of the anode. The copper 2 ions can then plate out on the pure copper cathode, where those copper ions undergo reduction. Other ions, such as zinc, remain in the solution. This concludes this lecture on metallurgy. Remember, metallurgy has 3 processes: preliminary treatment, the concentration of a mineral, followed by reduction, taking the cationic metal and reducing it to oxidation state 0 to get a free metal, and finally refining.